to go after you. Bumblebees are kind of the SUVs of bees.
Oh, the SUV.
Yeah, it's they kind of meander. Because I know this because as a kid, we had a bumblebee nest under our shed, and I thought it would be great. We had a ping pong table in our backyard, and I thought it'd be a great idea to try to hit this bumblebee, which I can only assume was the queen, out of the air with the ping pong paddle. So after I missed, well, I hit it, but I didn't hurt it. So it chased me across the street. I almost got hit by traffic. End up getting stung in my armpit. But then from that point forward, my dad started tormenting me. He was telling me they were passing my picture around and stuff.
They were passing the picture.
Yeah, because every single time I came outside, they'd come out and start going after me.
Really?
And then we had the exterminator come out and spray under the shed where they were. And I went up and I started yelling at it, like taunting it. And like two came out and like just died.
Just died.
Yeah. But they still wanted to get me on their deathbed. I was their one goal. It was their one goal on the deathbed. All right, so I got to take a mental image of who gets full credit on their quizzes today. Okay, I got it. Everybody else gets zeros on quizzes. Where's everybody else? All right. Am I recording? I think I'm recording. Yes. Okay. So let's finish up our discussion of MVC and then go over to backend pretty quickly. We were talking last time about a technology like PHP and JSP and ASP.NET. These are all kind of, well, really Python. PHP is really kind of, I think, the starting point for this. This was kind of the OG languages built for building websites. Not that you can't use it for other things, but that's what people use it for. But as websites, this is in the very, very early days of the web. So as websites started getting more and more and more complex, as our computer programs started getting more complex, as we started to figure out different ways of bending the web to our will, as our internet connections got quicker, we started to think about, hey, let's have programs communicating with each other over the web, all these things. As our applications got more and more complex, our PHP documents started getting scary. Because inside the PHP document, you'd have all the HTML, JavaScript, the normal web page stuff. You'd have all of the JavaScript, or you'd have all the HTML, JavaScript, the normal stuff. Then you have all the PHP code embedded in there where it would say, okay, well, this section is going to get replaced with HTML and JavaScript, but because this is a PHP file and because this is tagged PHP right here in this section, we're going to send this code in, have it run, and when it comes back out, it's going to have answers. And the answer is going to be HTML, JavaScript, nowadays CSS, whatever. So you have a lot of different things embedded into this one document. You had your code behind, you had your logic, your controller you had behind the scenes. You had your management of your data, your models, not so much embedded, but your database calls were happening inside of that document, as well as your user interface. So PHP is your back end. User interface, HTML, JavaScript is your front end. And you had this database sitting somewhere, whether it's locally on the computer you're at or somewhere up in the cloud. We didn't call it cloud then. We just said a server running somewhere. Cloud came later when we needed to come up with a fluffy, easily understood thing for normal people to understand what it means to have servers sitting out there somewhere else on the internet listening for incoming calls. We just call it the cloud. And now we could just say, oh, things are in the cloud, and that means something to normal people who don't need to know how these things work. All right, so to move this to modern vernacular, where's my plus sign? There we go.
So JSP and ASP.NET.
They came after PHP. JSP is the Java technology, Java server pages. ASP.NET is the Microsoft version of PHP. You can think of it that way. And it's embedded into Visual Studio, so you can build your websites using drag and drop user interface stuff. but that's really kind of not as handy as it might sound like it is, because HTML5, you could do some pretty cool stuff with it, just writing HTML5 stuff. Whereas if you're building your user interface using Visual Studio, you're bringing in a lot of the same kind of components that you use to build normal Windows applications, you know, buttons and drop downs, and but things that are made for a desktop application, not necessarily a modern webby looking thing. So I'm not sure it gives you as much advantage as you might think. Most people who would make ASP.NET sites, they might spend a lot of time just embedding HTML they created on some other tool into their application to get it looking the way they want it to look, rather than building with Visual Studio's um, own graphic user interface builder. Um, Typically, people who are writing ASP.NET stuff are in a Microsoft ecosystem where the web server at that place is a IIS web server, Internet Information Server, which is Microsoft's, let's call it, enterprise competitor with Apache. Apache is, let's call it, the de facto web server that's out there. If you're running Linux or Unix, well, everybody's running Linux now. If you're running Linux to host your web stuff, you're running Apache, or you're running an Apache wrapper. Nginx, there's a couple of different tools that effectively take the Apache backend and turn it into more of a real-timey type thing, but it's Apache, or Apache-esque. Let's go that. We haven't gotten far from the all right. So client server. So client server is kind of a networking model, where we have clients like our computers here, and then you have servers that live somewhere else. And the servers are doing something on our behalf and sending us the results, and then we decide what to do with these results when we're on when it comes back to us. So if we think about this from the web perspective, uh, we uh, we send across requests. Those requests get processed, whether it's PHP, whether it's just a backend. You know, a lot of modern websites don't even come close to embedding in between themselves. They use one technology as their backend. It might just be computer programs that are running. You know, could be a Python server, could be a Node.js server, which is JavaScript. But these are servers that are sitting there, and they're full big boy servers. They're not just HTML, JavaScript. They have these things called endpoints. They're APIs that have endpoints, like we talked about with the Pokemon thing. So these are like the next version of these things. It's like writing your own web server, but it's not just serving HTML and JavaScript. It's serving information, usually in JSON, like we saw. And then we can do with that information what we want in our websites, usually with the local JavaScript making that call. So you can have your local JavaScript making the call to a server that's Python or Node.js. Those are your two popular ones right now for people like us to spin up our own local servers to do stuff. But even people like us who want to create like a client server model, like we're going to have an application. I think I showed this previously. Do I have it up here? Let's just see if I have I think this one is that up. Okay. So for example, this site right here is a tool I've made for like my ministry stuff and Bible study stuff and things like that. But this is running on a Python server. So this website, when it loads stuff, so notice here in the URL, it's just here's my base thing /web server, blah blah blah. Nothing else after that. So this is the end of it right here. If I go and I click on here, this is the stuff that deals with Paul. If I clicked on that, I'm on a different, from our perspective, there's brand new stuff here. But if I come up here, notice that the URL has not changed. Nothing has changed on the URL. I haven't gone to a new file, because what's being displayed here is completely being generated by this server that's running somewhere. So when I first developed this, I run it on a local server running locally on my computer. I test it, make sure. So I would be hitting local host at port 4002 or something like that. Your computers themselves have all these little ports. You can think of them as like phone extensions. You dial into a phone bank and say, if you know the extension of your party, please dial it now. Yeah. You dial into your computer IP address, and then if you know the port where the application you're trying to reach is running on and where he's listening, you can enter it now. Well, you kind of have to, with computer stuff. So you'll say, so this guy is running on the cloud, awesomefat.com, which is one of my servers, which actually lives in my basement server rack, server closet thing. So it's a networking thing. You get that to work from behind your cable modem. So I do DMZ and port forwarding stuff to make all that work. But so I'm running that locally on my own local consumerish hardware. So realistically speaking, I wouldn't give this out to 10,000 people. I give this out to 20, 30 people who, at most you're going to have what, 0 to 3 people using it at once. They check it out once, they don't come back. Yeah, it looks cool, but whatever, out of sight, out of mind. But, that machine is not going to be able to handle 4 zillion connections at once. But the way this is working, since you just saw it doesn't change pages, this HTML page, when I click something, JavaScript is receiving that request. All right, it's receiving that request. It's then talking to in this case, this is a Python server. So there's a Python server running on this computer that's in my house, or when I'm testing it, it's just running locally on this computer. So it's running at localhost port 4002, 4008, whatever it is. So when I'm testing it, it's doing that. But you have the server that it takes in requests. It says, hey, I need all the stuff dealing with the book of Mark, whatever that is. So /Mark stuff. Awesomefat.com's colon 4002 /Bible Explorer, blah, blah, blah. And then we hit the endpoint for Mark stuff, and it sent back JSON with all the Mark stuff in it. The JavaScript running in the website then received that JSON and took all the stuff out of it and made this page. All right, that's why the site didn't change, the content did. All right, so we're seeing this whole client server model. This is our user interface, MVC. This is our view. Okay, our controller is that Python program that's listening for our requests or whatever, and it is dictating what we currently see on the screen. All right, then the model part of this would be the database where this stuff is stored. In this particular application, I use Google's backend database called Firestore. Firebase is kind of their cloud. So you can log into this site and so you can favorite stuff. And now when I favorite stuff, it's getting stored in Google's Firestore, which is on one of Google's data centers somewhere, if you want to connect it to this Port Washington data center. When you think cloud, we think up, but really it's probably some farmland somewhere near a lake. That's the reality. Why is it near a lake? Because they get hot. And there's lots of water in lakes to cool off the hot things. But then you put hot water back into the lakes and kill the fish. So that's called a fish boil. So people pay top dollar for that kind of lunch.
Might have a weird smelling, meat, but hey, it's cheaper.
Yeah. But anyways, then that's when you start getting the eco-friendly people out. Hey, let's not ruin our ecosystem, blah, blah, blah. So now we have to look at different ways of cooling this hardware, because I think we can all agree that human beings aren't going to stop wanting stuff to be fast. That's not how we work, right? We're willing to destroy our environment at the end of the day, as long as it's fast. Now, we'll take a couple of steps. We'll spend a little bit of money to protect the environment. Well, I guess it depends on who's running the show. If there's a super, rich place who just says, look, you're building this, I want it as cheap as possible. I don't care what you have to kill. We'll pay off the government. Unfortunately, that probably happens a lot. But anyways, that's this whole client server model. So when you think cloud, it's generally not up. It's running in some giant server farm somewhere that we now call data centers. Just a whole bunch of computers that are networked together. So it's almost like one gigantic bank of when you see something that says compute. If you're ever looking at cloud stuff, and you can either buy compute or you can buy storage, or so compute is stuff that runs on CPUs. So if you need number crunching and assembly language stuff, if statements, loops, things like that, all those things run on CPUs. They need compute power to do that. Then you have the storage side of things, and you get to choose the different kinds of storage. Some things you need for fast. You need it to be fast because you're going to be coming back to it often. So you want that stuff to be able to super quick. That's where you store it in, like in this case, Google's Firestore, which is a real-time database. But then they have this cold storage thing. So cold storage is a lot cheaper, but cold storage is stored on older, slower hardware. Usually you can get bigger hard drives. You go into like Amazon, for example, and you look up like an 8 terabyte hard drive, I think might be the biggest you can get as a single drive within reasonable reason. I think they do sell 16 terabyte ones, but let's just say you look at an 8 terabyte hard drive. An 8 terabyte hard drive is probably going to be from like, you'll see like something from like Western Digital or something like that. And yeah, let's say it's 400 and some odd dollars or something like that. Okay. But if you look for an 8 terabyte SSD, you won't find it. You'll find probably a maximum of 4 terabyte SSDs, and they're going to be stupid expensive. 2 terabyte SSDs are right at the edge when it becomes almost stupid expensive. 1 terabyte right now is your sweet spot for solid state drives. But solid state drives are significantly faster than old HDD. So whenever you see SSD versus HDD, you're thinking of the difference between solid state medium, which is like the same stuff that plugs in with the USB drive. There's no moving parts in that. And we keep coming up with better and better and better technology to make those faster and faster and faster and faster. But the old hard drive technology, HDD, had platters, and these were spinning disks inside of there, which means they are susceptible to things dropping. So when you had laptops with those drives in them, they had to have sensors in them to lock the drive in the event you like dropped the laptop or something like that. Because if you dropped it otherwise, I mean, it's almost like a record player looking thing. There's a little read head. And if you drop that thing and all of a sudden this thing goes, just smashes through all the platters, your data's gone. So then you have to do things like platter transplants, where you open it up and there's maybe like, depending on the technology, 8 to 20 platters in there, like little CDs piled on top of each other. You could take out the broken ones and then transplant the other ones into another drive that works, and see if you can resurrect part of that drive through another drive's mechanicals, like have it read the records and a different thing. So this is all digital forensic stuff. How do you recover data? Blah, blah, blah. SATA is the connections. This is back kind of to our Ethernet conversation. SATA is the interface between the back of the drive and the plug into your motherboard. So you'll have a SATA plug into the motherboard. SATA can go up, modern SATA, I think, can go up to 6 gigabits per second. Original SATA was 3 gigabits per second, which sounds fast, but that actually might be the slowdown for a lot of our drives. That's why newer, they're still technically solid state technologies, but you'll see them as M2, NVMe drives. Those plug in differently. They plug in directly to the motherboard through an NVMe slot, and that interface is faster. Now, you're still, the technology and the drive still has to be able to cook at a fast enough speed to fully take advantage of that interface, but that interface is a faster interface than SATA. SATA, there are physical cables. If you've ever seen SATA, you've seen them probably laying around when somebody gets a new motherboard or something. They're usually like either like a red cable, and it's about, it looks like one of those big rubber bands, but it's probably 3 times thicker than a rubber band, but a kind of a similar width. Um, that's kind of the width of those cables, as opposed to the older IDE cables. For older HDDs, you'd have these gray flat cables, probably about the width of my finger here or so. They were ribbon cables, and when you plug it in, you'd have like 60 pins sitting there, and if you didn't have it perfectly centered, all of a sudden you bend the crap out of half the pins, and you got to get in there with needle nose pliers, and hopefully you don't break a pin off. Yeah, these are all, but definitely not from experience.
Essentially, tangent, just.
Yeah.
If you had 10 vinyl records stacked on top of each other, the reader head can't read the second one down. So how is it able to penetrate into those stacked discs?
Because there's multiple read heads.
Like,
Yeah, so it's kind of like interjected in there. So it hands off to the next reader. With solid state drives, there aren't moving parts, so everything's actually wired. So you can pull from it. And solid state's what allowed a lot of our modern computers get so small. Like you've probably seen the letters SOC next to each other before. Do you know what that means? SOC. It's system on a chip. So what it effectively is they've removed all those wires that hook things together, and they just soldered it all together. Like if you were to look inside this computer right here, this is, the highest end thing you can get from Apple. Well, highest thing you can get from Apple 3 months ago. The new highest thing comes Friday. But if you looked inside this, you would see relatively small part is the computer. The rest of it's battery. That's what's inside of this chassis here. Mostly battery. So we have systems on a chip where everything is just integrated, but that trade-off is they're not upgradable. You can't put more RAM in it because there isn't a such thing as RAM. It's just kind of all part of this soldered together monster.
As far as computers go, how like I start with you guys. Carson said to look at older ones, because those are the ones that you can upgrade more.
Well, it depends what you're trying to accomplish when you're looking at computers.
Laptop, like stuff.
Okay, well, do you have a reason to upgrade it?
Yeah, I run out of storage.
No. If you bought a new one, presumably are you buying it with the plan that you're going to upgrade it? Or are you buying it because you want this thing to be your daily for the next 3 years?
Yeah.
So you don't worry about upgradability. You buy a machine today that, especially if you're dealing with laptops, most laptops are not upgradable very much at all anymore. So you buy the machine today and you make sure you load it with enough stuff that's going to carry you through the next 3 years. So if you bought a computer today and you've got at least 32, if not 48 gigs of RAM in it, that probably will float you for 3 years in terms of being able to do stuff. Then you want to make sure you have if you buy today's budget pleaser CPU, it's not going to last you 3 years. You want to buy today's mid-tier CPU. So if you're on an Intel Windows side of things, you want to get probably at least an i5 processor. If you can swing it, a Core i7 is probably reasonable. Then they have some other low power ones. That depends if you're a traveler and do you need 18 hours of battery life, or if you have 5 hours of battery life, is that okay? So if you're going to play games on it, well, then you need one with a dedicated GPU because Intel embedded graphics is only going to get you so far. These are all the questions you have to answer. Upgradability, I would just throw out the window. That's not a thing anymore. I mean, people who build gaming PCs, you can say it's a thing, but the people who build gaming PCs and they want them fast, they think that upgradability means something. It's like, oh, I want to be able to put in 2 years the latest, greatest GPU. But in 2 years, your CPU is also outdated. So now it becomes the new hold up. Same thing, RAM. Yeah, you had enough RAM, but you don't have the latest, greatest, fastest RAM.
Yeah.
So are you going to really keep upgrading it, or do you want to get enough gaming PC today to play every game that you want to play, and then overbuild it a little bit so it kind of lasts you 2 more years, and you just pretend like those same games 2 years from now, you still want to be able to control them. But after that, you're pretty much building a whole new system anyways. Maybe you can keep your hard drives, because hard drives are only really important for when your game first loads and stuff's transferring from your hard drive into memory. So if your hard drive is slow and all you're doing for the thing is playing games, your games will launch slower, but once it's launched, it should be pretty decent. Cutscenes sometimes will be slower because it usually loads the next level from hard drive, but performance while playing is reasonable. All right, so client server says we have a client program talking to a server program, which is just a piece of software running on a computer, could even be the same computer. Which is super common if you are running, testing your stuff locally before you deploy it somewhere. But it's a two-person job. You have your user interface typically somewhere. Like we just saw that Bible website. That's my user interface into my computer program. The computer program is running on a server, running Python, just listening for you to call these endpoints. And these endpoints are kind of a fancy way of saying, hey, how do I call functions that live on this server by way of a connection from the internet? So when you connect to this point / do something endpoint, it's calling a function behind the scenes to actually process what it means for that endpoint, right? So these APIs, these endpoint things are just your mechanism for making different function calls into that server that's running somewhere. And we give it fancy names and whatever, blah, blah, blah. All right. So what I want to do here is let's just kind of start building this out instead of talking about it as much. So I'm going to go ahead and I'm going to create my 3D. I just opened up a new project, our dungeon crawler, because we're starting to move towards that. So I'm going to create my floor. Okay, so there's my floor. I'm then going to go ahead and create my my dude. So we'll have our dude be so this is our player. All right, he's already, let's see, I think he's sunk down half, right?
Yeah, no, I think he's elevated,
Really?
right? No, you were right.
Let's find out. Now you know. All right, so 0.5 gets it where it was at. But now you know why at the beginning of the Mario game they start him above the ground and have him drop it. They don't have to have him pixel perfect. Just drop him in until there's a collision. Now he's on the ground. Easy peasy. All right, so we have this guy here. And then last time we had looked at like a placeholder. So we're going to kind of go through the homework assignment and then expand it from there. So we're looking for a placeholder. So I'm going to zoom back out. And we're going to put a empty game object. And we're going to call this guy the drop point. All right, and we'll throw him way up here in the sky. We'll actually start him in a place where we can maybe see him. Then we'll move him up once we see it working. So just for the moment, I'm going to just hang a cube off him. There we go. So my actual game object's called drop point. That's this invisible game object. And I just nested within him a cube currently. so I can visually see where he's at on the screen, because game objects, they hide very well when they have no renderer. So when you're just a transform, humans don't get to see them. So very commonly, I'll hang something off it temporarily, so when I'm maneuvering it, I can see what's going on, and then you could either remove it or just hide the thing, disable the thing. Little kind of tricks that you run into, otherwise you start losing game objects, because these drop points are kind of fairly common. All right, so we're going to go ahead. I'm going to create a folder here for my scripts. All right, so inside this folder, we'll go ahead and create a mono behavior script. And let's call this guy Rain the Fury. Rain the Fury. Man, my eyes are so, I need to get either readers or bifocal contacts, and I don't want to. That's the problem. All right. I need to make this bigger. On a Mac, you hit Command plus sign. I'm guessing it's Control plus sign on a PC.
The thing that you just tuck to the side.
Oh.
Try and increase my thing and get frustrated.
Aren't you guys supposed to be the ones who know how to use these, I don't know, newfangled? I don't use this crap. The thing I run into, and I bet you it's still enabled, is I don't like Copilot.
Like Copilot either, it breaks my heart.
Well, I use something more powerful than Copilot when I'm coding, but when I'm teaching it, I want you to see it done for real. Because ultimately what you want to do is you want to learn, how does this really work? Then once you feel like, okay, I have enough understanding of this, I could write this myself if I really wanted to, but I don't want to. That's when you let the AIs and copilots and those things take over. So I'd encourage you to disable it initially when you're coding in here, and not let it do too much for you here. But maybe use like ChatGPT external to this. If you have a question like, hey, how do I do this? Let it show you the 5 or 6 lines of code, so you can like, oh, okay, that's it. And you can embed it in there by hand. But it's going to be so easy for you to just see something. Oh, that's right. Hit tab. But you've learned nothing from those 7 lines that just got dropped in. But hey, I don't know, it gets in my way. I don't like it. And then I always have to say, how do we get rid of it? And then nobody knows the answer, but blah, it's terrible. Oh, I'm sure I could figure it out. It's more of just the real time, the real time situation. All right. So again, MVC says it's a good idea to keep your data separated from your user interface, separated from your controller, your brains behind the operation, the if statements, the loops, all those things. All right. So right here, we're looking at which part of this is out of the MVC. Which part are we looking at right here? The M, the V, or the C? C. This is controller. So we think of controllers like your remote control, except instead of that, us using a manual remote control, we're using a computer program to control our stuff. This is our controller. All right. So I, though, want to have control over a particular game object here. And I need to, actually, I'm going to need control over a couple of game objects, but let's start with one. So I want control of that drop point. Now, the drop point is something that we designed on this part out here. So out of the MVC, what am I looking at here? The M, the V, or the C? This is the V. All right. So if I want to get something from code exported out to here, I then need to do something to it in code. And the way MVC, as you've already seen, works is all we do is we put public in front of it in Unity. So that immediately says, I'm going to expose this variable to something that lives out in the view side of things. So we're going to call this guy, he's going to be a game object. We're going to call him drop point, call him whatever you want. Now what I usually do, so I don't forget, as soon as I create a public thing, I jump over and I wire it up. Because all I've done right now is I said, I now have exposed a variable to the view side of things. But until I actually connect a real thing from the view to that variable, I'm not actually controlling anything. I just have the ability to control something. Good.
So I know that game object creates the game object, but like it also.
It doesn't create anything. This is a variable. This is just a plain Jane variable, just like I said, public int age, or what did you, why? I don't want you to do any of that stuff. Public int age, same thing as that. Just a variable.
So that would be plug values in, that does that, but I don't know why.
Well, you come out here and this is the script where that stuff lives. So we want that script to live on our drop point. So I'll go ahead and drag that component out here, and notice here we now have a game object called drop point, and we have age, that variable I just created. So I can put both of those guys on here. Okay, but now if we attach this script to the drop point, do we actually need to connect up our drop point? Or does the script already know about this .game object, the game object that owns that script? He already knows about it. Okay, so we actually don't need either of these lines right now. I'm going to keep the first line in there, and we're going to call this, we'll call this the drop object. That is the thing in which we want to, the thing that we wish to drop. That's what that guy is. All right, so we already have access to the drop place because that's the thing that this script is attached to. So that's this .game object. But I need to, what are you doing? Ninja, click. All right, nailed it. All right, so I'm going to go ahead and we're going to create our bad guy. So we'll create a 3D object. What did I say? Ring cubes?
Yeah.
I said ring cubes.
Wait,
That is
green,
spheres.
green, red.
Whatever. What are your bad guys? Spheres? You had spheres bouncing off of spheres?
Oh,
Okay, that's fine.
Spheres bound.
All right, but we're gonna make them different color spheres at least, right? All right. So we're gonna call this guy bad. Ooh, goad. Okay, so bad guy, bad guy. That's good enough. All right, so here's this guy. I'm gonna go ahead and let's just give him a color. So we'll create just to keep with good programming practice, we'll create a folder for our materials. You don't have to. You can put all your world's crap into your assets folder and just live with it. Try to be a little organized because just like as we've been talking with PHP, as this gets more and more crazy, all of a sudden you're going to have a wall of stuff. You kind of want to have a place to go for it. So here's my materials folder. I'll go in there. I'll right click. I'll create a material. Here's my material. I'll click on this, which is is this my color? Where's my color? This guy?
Oh, yeah.
I don't want to do that. It's the who? Oh, there we go. And I like a reddish one. Ooh, an orangey one. Ah, that looks pretty. All right, that's my material. So I'll just drop that guy. Oh, that's supposed to be the bad guy. I don't want him on there. All right, so bad guy. Oh, we need to get the bad guy elevated a little bit so I can hit him. Then we'll put him where we want him. All right, so that's the bad guy. We'll say the good guy. We'll create a new material. And we'll make this guy here, greenish. That way we can tell good guys from bad guys. Oh, and then we should go ahead and create another material for the ground. And we'll say our ground is kind of like a concrete-y color. Oh, sorry. Did it even change color? No.
Yes.
I think it'll,
So then we're gonna make the ground bluish. There we go. All right. So we have that. Let's go ahead and get our bad guy. Now, I'm actually, just for the sake of argument here, I'm going to take away my cube I built up here, and I'm going to just inlay the bad guy with our drop point. Now, well, the cube was only there for me to visually see. Now I have a bad guy to visually see that I'm going to hide because I'm going to spawn bad guys.
Oh.
But in order for me to have my original bad guy, the model of the dude in which I wish to spawn, I need to get him in the scene somehow. It's actually only half true. You could do it completely programmatically, but this is the easier way of doing it. So I'll go ahead and I'm gonna click on my bad guy here, and I'm going to change his X, Y, and Z to 0, 0, 0. But now you'll notice that my good guy here is at basically position 0, 0, 0 with the 0.5 being above it. So if I want to put him actually at 0, 0, 0, just for the sake of argument, I'll put this guy at 0. I'll put this guy at 0. And we know this is basically 0. We just didn't want him sitting on the floor, right? So he's at 0, 0, 0, yet my bad guy here is at 0, 0, 0, yet we don't see him on the screen. We see him up here. How can they both be 0, 0, 0 and be at different points?
Based on your starting, like you gave him the starting position of being locked into that starting position.
Yeah. So your transform is relative to your parent.
Yes.
So our bad guy's parent is drop point. So 0, 0, 0 says my offset from my parent is nothing. I exist at the exact place my parent exists.
If you go into drop point, what did it say?
Drop point will be whatever Y is above the ground, 4.15, blah, blah, blah. Here, I'll get him centered nicely above the other guy since we moved the other guy. He's just higher up in the air right now, but directly above the other guy because we wanted to do some random number-y stuff to zig and zag so he bounces off the sphere some.
So it feels like that could get confusing if you were compounding things within things to try to remember where.
Well, and the thing is, you don't have to do that. Usually you compound things inside of things when you want to do something like that, or it's when you're literally trying to organize stuff. So like, for instance, when we build our rooms and we're going to start making walls, you might create a empty game object like a folder to hold all your walls, yet you'll go, so when you first drop your wall in, it'll be where that empty folder is that you just put off to the side somewhere. But ultimately, you're going to drag them into a location that's going to build your wall. So yes, it's relative to that game object, but that game object isn't an important thing anymore. Although by having it under there, other than organization, you can now move that game object and move all your walls at once around. So if you decide you want your entire room to be shifted, you don't have to shift one wall at a time. You just have to move that top level game object and everything will move with it. So other benefits from it. All right. So I'm going to go back to my my drop point here. This is the guy that has the public stuff in it. I'm going to go ahead and take out my oops, sorry. So my drop point wants to know about the drop object. Now, technically, I could programmatically find this drop object since it's part of his transform now. It's a child of it. But let's not be ridiculous and say, I want to have convenient access to the dude I want to create instances of. So I'll drag him in there. All right. Now, for right now, let's just look at what we're seeing here. None of these guys have rigid bodies or anything like that. Now, ultimately, we would like our bad guys to hit our player and interact, bounce off physics, blah, blah, blah. So in order for those things to happen, we have to have something fall off out of the sky. All right. So now remember that if I look at my player here, my player has a mesh renderer. We can see him. He has a sphere collider, which means he can collide with stuff. Colliders collide with colliders. All right. So you do not need a rigid body to collide. You need a rigid body for physics to be a thing. All right. So let's leave our player alone for right now. He doesn't need a rigid body. He just needs to be able to have things hit him. But let's go ahead. You know, if I run it is running right now. So we see our bad guys hanging up in the sky. But if I go to my bad guy and I drop in a rigid body and I make sure gravity is turned on and then I hit play, now the red thing will fall out of the sky and perfectly hit, right? That's the thing we were trying to avoid is we don't want him to perfectly hit. We want it to be just teeny bit off. So if I go into my bad guy and I change the X to 0.2 or something like that, and then I drop it. All right, so
When they date cut, you can also make it bouncy, but I found out.
yeah, I'm sure because you're messing with all these different things in here and how they interact with each other. They will actually interact with each other differently if we put a rigid body on the base here, because now you have two different masses that physics takes into consideration. Now, not being a moving mass, I don't know if we'd actually be able to see the difference, but let's test it real quick. So we'll just set a player, we'll give him a rigid body. We don't even need to turn off gravity because he's already sitting on the ground, but we might say that gravity is a waste of time, but I don't want to click the button. All right, so now you see how he's moving. Okay, because now physics works on him now that he has a rigid body. Now, because we want to be raining down on top of this guy, we don't want him to do a lot of wandering. We can either turn physics off for him, which means remove the rigid body, or we can do some things like constraints. So we can put constraints on certain X, Y's, and Z's. Let's see, where's the constraint thing? I might have to go and look that up for another. You put locks on the individual things. Is it under our collider? Oh, constraints under rigid body. So I can freeze the X, the Y, and the Z on the player.
Or position.
That's for position, yeah. So now, even though physics is there, he can't go anywhere. Now, at that point, you might say, okay, well, why does he have a rigid body at all? I would certainly say that. So for a player, we're just going to dump the rigid body. He doesn't need one in this case.
Is that kind of like if you were playing a game, like hypothetically game, and like instead of having an object that's not with no physics, would have physics on it, so it would like kind of do something, but it wouldn't really move.
Well, okay, so like as an example, let's go back and put the rigid body back on this guy. I'll go down and let's just say I'm going to freeze him on the Z and the Y. So I'm sorry, he's frozen on the X, but he can go to the Z and he can go to the Y. And I think my drop currently makes him try to go on the X, so he won't move still. Okay, so let's switch the X and the Z. Or X and Y rather. All right, so now he can slide on the X, but he can't slide on the Y or the Z. So I'll make it so that he will now go to the left a little bit. See him rolling? Just a little bit. All right, so now we're going to go ahead and take our drop guy and we're going to make him negative 0.2. So he'll hit the other side of it to try to smush it the other way. And now he won't be able to move because I've constrained that direction.
I think it's still right.
Why are you moving?
Because you have to go negative.
Oh, hold on. Did I turn the stuff off when it was still running?
No, it's that I think you have to go, if you go to your.
Yeah, let me just confirm constraints real quick. Okay, there we go. So my bad guy moved it the wrong direction. That's what we're saying.
I think you have to put that at 0 and then put Y at 2.
Oh,
Or -1.
Or is it C? Because C moves forward and backwards.
oh, yeah, yeah.
Oh, that, then,
Yeah, you know what we're gonna do? We're gonna do this. All right, we want him to move the other direction. All right, so he's moving positive, right?
Oh, that's still-
yeah.
Yeah, but we want to hit him on the other side.
Are you trying to get him to move on?
Oh, where was he moving before? So moving before, he was moving.
Side to side. It turns the blue. Side to black.
Well, the blue is the ground.
Oh, it is?
Yeah. Okay. So that he's going that way now. So now I'll just move him the other direction.
The blue arrow.
Oh, the blue arrow is, I thought, the Z.
Still.
Okay. So now he's moving in the direction I want him to go. So the question is, why is he moving?
Because you enable X. This works for both sides.
Oh, you're right. X does move both ways. See, I was testing you. So really what you want me to do, now I get what you were saying. Oh, not that guy. You're late. You missed the quiz. We had a quiz.
You know what?
Yeah. At 2 a.m.
Well, it wasn't a quiz day before I knew nobody was showing up.
Well, I think
All right.
Oh, so it doesn't ever line.
Yeah. All right. But regardless, we get the point of the constraints. All right. So let's put our guy back up here. Let's get him back at 0, 0. So he's because we're going to use this guy. We're going to use this guy as our kind of our model for our dude we're going to drop. We could even have him drop first if we wanted to, if we didn't want to just purely use him as a model, but I probably will just use him as a model. All right, so all right, let's see. Where's my script? Player, close, player, script, ninja. Oh, he's the script's on drop point, right? All right. So our drop object is our bad guy. So he's the guy we want to actually drop. So what I'll actually do for I'm going to leave the bad guy on for a second. We'll go back over to our code because now what we want to do is we want to create instances of our guy at that place. So we already know our location. Our location, we know we can get to by saying this dot transform. I like saying this dot game object dot transform. All right. Oh man, lots of people showing up and missing quizzes. Terrible. All right, so we're going to say this. Well, actually, we're going to say instantiate. All right, so now instantiate. What parameters does this guy take? Unity instantiate. Key. There's one where it gives you an instance of something, and then also the transform where you want to start. Okay. So we have an instantiate. You give it the original object, and it just creates another instance right there. So we can go ahead and actually just do that real quick. So we'll instantiate this dot drop object. All right, this is going to happen one time at start. So if we already have one drop object and we're instantiating another version of that drop object, we should have two of those drop objects. All right, I don't remember what we have constraints set at now, but this will be fun any way you cut it. In fact, I'm just going to go to my player. We're going to remove the rigid body from player. We don't need it in this case. We do want rigid body on bad guy because he wants to fall out of the sky, so he has to have gravity. So what we expect to happen right here at the beginning is we've already seen our main bad guy dropping, but now when our script for drop point spins up. During start, he's going to create another instance of our bad guy who has a rigid body who's going to start dropping.
Do we ever set the for it?
The point for it is the same point as he was at.
Oh, okay, so we don't need to create a.
Yeah. So, but tell me here. So watch it closely. Did you notice that one of the guys had already dropped? He was already bouncing off. All right, so we're going to take instantiate out of there because start happens before things are visible. All right, so we're going to take it out of there. So now what we want to do is we want to have a new thing drop every so often. All right, so how do we create a timing to make something happen, let's say every 1 second? How do I determine if 1 second has occurred? So let me show you something here. So I'm going to do a print. Can't I print here? Yeah, print. It'll be out at our console. Actually, where will the console be? It'll be on here. Not only if I connect it. Oh, I'll try it. All right, so we're going to print this dot time dot, was it? No, it's just time dot delta time. All right, so what is time dot delta time? If you were to explain that to me, what is time dot delta time? Go ahead.
Is time dot delta time kind of like unit equals to real time? I guess you could say like our current time.
Okay, but specifically, what is delta time? Time allows us to access time. All right, but what is delta time? Go ahead. Yeah. So if you've had physics classes and stuff like that, usually when you see the Greek letter delta, looks like a triangle-y looking thing, that's the change in something. So delta time is the change in time since the last time this guy was called. All right, so I won't even do the print. We can just imagine, okay, if the last time this guy was called happened, some 2 seconds ago, or happened, if we're putting in an update, how often is it going to happen? A lot. If we do fixed update, it'll happen 60 times a second. But we want to ask whether delta time has reached a certain point. So if time dot delta time, let's say, is well, let's just go this route, is greater than 1.
1 being second.
I think I need to do it 1,000. Is it?
I think it's 1,000.
Is so we're going to say if time dot delta time is greater than 1,000. Well, we'll find out pretty quick. Then we'll create instantiate. This dot, what is our guy called? Drop object. And here, just real quick, let me just do a unity time dot delta time. Let's make sure we're using it right. Okay, this is when you use it in for rotating stuff. That's probably where you used it in your tutorial for the little guys who are spinning a little bit. So you use the change in time between frames to nudge it just a little bit in each direction. But since frames are happening so often, it's occurring at different things. Okay, so here's like an example of waiting for time or having a timer. So in update, we're building up a timer. Then we're asking a question if timer is greater than wait time. If it is, then we do something and then we decrement that from timer so we can get back up to that. So we're collecting time inside of a float. All right, so, and we'll do that since we need a timer for this. So we'll go ahead and we'll create a private float We'll call it timer. We'll start this off at 0.0 F. Wait, was it lowercase f? There we go. Why do we put F there? Why do I need F after the 0.0? Why can't I just say 0.0?
Because it won't take.
Well, that's true. Floats can't hold integers, but is 0.0 an integer?
Well,
Is it? What's an integer? A whole number, right? Zero is an integer. 4 is an integer. But is 4.2 an integer? Is 4.0 an integer? No, those are all floating point numbers.
like,
But why do I have to put F after this guy? It's clearly not happy if I don't put F next to it. Why? It's a float. It only truncates if you're trying to make it an int. It'll certainly truncate it if I say int here. It's going to tell me that you can't hold that. But if I force that guy, if I say, okay, look, trust me, you are an int. Now it's truncated. 0.0 just became 0. Okay, or 1.99 becomes a 1 if you truncate. But I'm not dealing with ints. I'm dealing with floats. Why is it not happy with me putting 0.0 inside of a float? Why do I have to put an F on there for it to work? You have all the information you need to answer this question. I probably answered it in some discussion in coding 1.
the program doesn't know that. It's a float. To tell it that.
Why? You're right, but why?
Uh,
What other things can 0.0 be in a modern programming language? Are there any other ways of holding floating point values in modern programming languages? Whether it's Java or what's the difference between a float and a double? Okay, so we weren't listening in coding 1. What's the difference between a float and a double? What's the difference between a byte, a short, an int, and a long? Let's go with that one. See if we were listening on that one. Go ahead. Okay. Not the type of information though, right? Byte, short, int, long are all built for holding integer values. So the type of information is all the same. All right. But the second thing you said is what? How much stuff fits in there. Because a byte is only 8 bits. So we can only hold, now are bytes signed or unsigned? What do I mean when I say signed or unsigned? Why are we reviewing week 4 of coding 1? Okay, a signed value can hold negative and positive numbers, which means that if we have bytes, if we have 8 bits and we want that guy to be signed, we have to use one of those bits to control sign. So that means we actually only get magnitude out of the 7 bits, which is plus or minus, well, 7 bits, you can hold a value of 128. All right. So it's 2 to the 7th power. 2 to the 8th power is 256. All right. So, which means that in order for me to, what's the range of values that fits in a byte? Let's see if we remember this one. Oh, what's the name? What's the range of values that fits inside of a byte integer type in modern programming languages if it holds signed values? So I only get 7 bits of those. But what's the range of values? Negative what to positive what? Go ahead. Yes, why?
I can't remember why, but.
Zero.
Yeah, what about 0?
It exists, like, as opposed to sort of standard math is taking it as a 0. We use that 0 till.
Okay, almost.
We count 0, so technically, like, our last number isn't really our last number.
Do we need a positive and a negative 0? Or is 0 just 0? 0 is just 0. So if I have an 8-bit value, I can hold 256 unique states in an 8-bit value. We want to start thinking about things like that, not like, hey, this is always a number. It's how many things are we representing? I can only hold 256 unique states. If I want to hold negative numbers, I still can only hold 256 unique states, but now some of those states are going to be flagged as positive or negative, so I'm going to use 1 bit for that. Go ahead.
So why does it care that we have to specify it as a float if both float and double? Shouldn't the
Yeah,
problem?
we're getting there.
Shouldn't the problem only come about when we need a double, but we're using a float, so our stuff is too big for our bag, then it should yell at us.
You're not wrong, but this ultimately comes down to if you are holding whole numbers in modern programming languages, even if you know it's not going to get above the number 10, you would still store it in an int. Modernly, because we don't care about memory, we don't care very much about being as efficient as possible. So we just store it in an int. Well, if we're on a floating point side, we just store it in a double. So double is our default thing on the floating point side, which means that if we want to actually store it as a float, you have to tell it that this literal here, 0.0, is actually a floating point value literal. Otherwise, we will assume it's a double literal value.
Okay.
So we have to mark it as such in order, or otherwise the language won't be happy with it. Now we could always just say, look, screw it. We'll just make it a double. Now he said he's happy again. So why not just make it a double? Double made the red squiggly go away. Isn't that how we all code? Just keep changing crap till the squigglies disappear. That's how I code. I spend hours in front of these things. Like, why is the squiggly still there? Why does Copilot keep popping up? I'm not very good at using computers. These are rough things for me. Well, isn't that what they say? Those who can't do teach.
Those who can't do teach.
Yeah, it's like the saying for professors.
Oh,
Those who can't do teach.
oh. Wow.
So my level of incompetence has really locked me into the classroom.
Wow.
That's what you think about that when you walk into some of your other classes. All right. We have lots of really good professors here, but we got some that aren't. So what? Go ahead. Sorry.
Just be memory that we're trying to default to float as opposed to double. I mean, is there another reason that we would want?
Well, okay. So we've answered the final question. Let's go back to the ramp up. Okay. So she told us that we can hold different size values. She said signed means we can hold positive and negative. So we want a data type that can hold negative values and positive values. Okay, sounds reasonable enough. Okay, out of curiosity, why are chars unsigned integer types? Remind me of that. And then next time you see Professor Kellogg, ask him to explain Unicode to you. So I had to give him the same lecture with Panera a month ago or something.
You can't hold a negative letter unless you're expressing it as separate.
Negative letter. Ooh. I haven't heard that one before. Let's jump down that hole. All right, what is Unicode used for?
Why variety?
Okay, so we have a character set. The previous character set was ASCII. Then we had Unicode. ASCII is 256 unique characters. Haha, 8 bits. Unicode is a superset of ASCII that uses 16 bits. How many unique characters in Unicode? Thousands. What's the precise number? Do the math in your head. 2 to the 16th power. What is 2 to the 16th power? 65,536. Do you guys even take math? Do they take math anymore? I'm just teasing. You don't have to have that memorized. Remember, those who can't do teach, so we have to memorize stuff like that to make us sound smart. All right, so 2 to the 16th, 2 to the 8th, 2 to the 7th. Those are precise answers too. You don't have to do the math. Why do we have scientific notation? So we don't have to write big, scary, long numbers. How many unique values are stored inside of an unsigned 29-bit number? 2 to the 29th power. That's the number of unique states that 29 bits can store. How we use those states is up to us. In this case, we're using them as numbers. All right. So a byte is negative 128 to positive 127. Why does it have one extra thing on the negative side and one less thing on the positive side? Now, we already said we don't need to hold a positive and a negative 0. So how are negative numbers ever? Who is in computer architecture right now? Okay. How do we encode negative numbers? Good.
Don't you pretty much just add like?
Typically, answers don't come in the form of questions. Don't you just? Okay, so you were saying you're going to add something. What do you want to add? Let's see if you're about to explain the process.
So, kind of what Professor Blake was telling us, that we don't.
I hope so. Okay, we hope it's in that
One
class.
plus negative. Let's just do 1 plus 1, but then we add like the negative, we multiply the negative by the 1, if that makes sense. So-
No, it doesn't.
No?
Well, you asked me if it made sense. I said, no, it doesn't make sense. Go ahead. Two's complement, exactly. You probably originally saw one's complement. One's complement is where he introduces the problem. One's complement is when you flip all the bits and don't do it. Well, actually, before you, oh, what? We're going to get this in 15 seconds. One's complement, well, before one's complement, you used a single bit for magnitude, just a 1 or a 0 at the beginning. One's complement artificially gives you a negative 0 and a positive 0. Two's complement gives us a single 0, which means we get one extra value. Because remember, we have, with 8 bits, we have 2 to the 8th power of unique states, which means we have 256 unique values we can hold. Negative 128 all the way to 0, and then 0 to 127 is 256 unique states. We just didn't use a positive and a negative 0, so we got one extra one on the negative side because that's how the math works. When you decode two's complement, only negative numbers get encoded. So when you see an encoded value that starts with a 1, you know that's a negative number. So you just say, okay, this is going to be negative, then you decode two's complement to get the value. And you put a negative sign in front of it. That's my answer. Make sense? So we have to put F after this guy if we're going to store it as a float. The reason it's floats is most of these things, the back end is written in old C. And C typically used floats way back then because guess what? Doubles take up a lot more memory than floats do, just like ints take up more memory than bytes. So you can think of doubles kind of like longs and floats kind of like ints. But that makes it kind of interesting because we choose int as our default, yet we choose double as our default. Why? Because typically we want high precision when we're dealing with floating point values, that we give ourselves more bits. All right, questions, comments, concerns, bribes. Front row chapel.